Problem 689, maximum number of three non-overlapping subarrays. We are given what integer array nums and integer k. We need to find three non-overlapping subarrays of length k which has maximum sum m. Here they are asked that we do not have to return the sum, but instead we need to return the number of indices. So actually what they are saying, suppose we are given one array and we need to find three subarrays that after adding them our sum should be maximum. So let's understand that this we have given 1, 1, 2, 1, 2, 6, 7, 5, and 6, 7, 5, and 1. So what they have to choose, we need to choose any k subarrays. Here k they have mentioned. So for our example, let's suppose k2. So we need to take two element in a subarray. Like suppose we have chosen 1, 3. This is one subarray, and another subarray can we say just 6, 7, another subarray, and this is 5, 1. And if we add this, then we got one sum, and like this we can form another combinations, right? Like suppose we can, but there should be subarray, right? I mean we can't choose something like this, this like this 1, 6. This is not correct. This one and this we can't choose. So we should choose that element should be a subarray. The possible combination can be like this. Suppose you can choose 2, 1, and another can be this 2, 1 we can choose, and suppose we have chosen this 2, 6. And another 2, 6, and another can be suppose something like 7, 5. Like this. This is another combination. This will give us one sum. Right. So what is saying, like this will give 3 plus 13, and this will be something like 6. So it will give 6, 3, 9, 22. This part, and this one gives 2, 8, and 12. So what it will give, 12 and 20, 23. So obviously this is better. Like and our answer will be 1, 2, 2, 6, 7, 5. So what they have given answer 1, 2, 2, 6, 7, 5, 1, 2, 2, 6, and 7, 5. And this is our answer. This is one of the subarray. So this is same exactly 3 plus 8 plus 5, 12. This is also 23. But we need to return this because it is lexicographically smaller, right? Because 2, 1 if we see before solving this problem, let's solve one of the like basic subset sum problem. I mean we can draw the tree of that. Suppose this is one array and we need to find the max subset sum of this. Let's forget this problem like for a moment what they have given. Let's solve this first. The subset sum of the subarray, max subset sum. So how we solve this problem? Like we can have, so for each number we have a choice, right? Whether to include in that subset or whether to not include that subset, right? So let's start. We can take at 3. So 3 will be added, and rest of the number will be 4, 5. Like that is remaining. And if we take here, then sum will be 0, and rest of the number will be 5. Again, if we branch it into 2 choices, now 4 have 2 choices, whether to include into the sum or do not include into the sum. So suppose 4 got included, so sum will become -1, and the remaining numbers are 5. And if 4 is not get included, then sum will remain 3 itself, but this subset, the carry became 5 for the next question to pass. And if we move here, we can see if we include -4, then this will be the sum and this will be next remaining. And if we see here what it remains, if we can see, so if we don't include 4, then this will be 5 only. Again, if we branch it out, so we can see here it will be 4, right? -1 plus 5, 4. And if we don't take 5, then it will remain -1 itself. Again, if we branch it out for 5, so if we can say, then it is 8, and if we don't branch it out, then it will remain 3. Again, if we branch it out, then it will remain 1 itself, otherwise it will be -4. And similarly for this 5, if we branch it out, 5, and if we don't include it, then it will remain 0. Right, so we have used for like every element to include into the subset sum and to dot include the subset sum strategy to find the max subset sum. So if we look at the base, the last, so we get the 8 as the maximum sum, and the corresponding number that are responsible for that maximum sum are 3, 5. Right, these are the sum. If you see 3 and 5, so this could be the numbers that lead to this. Right. So if you look to this, what these numbers are, let's suppose if we, this is one subarray, right, of length 1, and this is another subarray of length 1. Right, this is one subarray of length 1, this is like another subarray of length 1, length equal to 1 for this subarray. So can't we use a similar technique like in our previous problem? But in that case, we have given that subarray should be of length k, right? So using the similar approach, we will also we have to take exactly one element every time. But here in our previous problem, we have to take k elements or 2 elements. And also they have given 3, means we need to form 3 subarrays. I mean something like this. Exactly we should choose 3 subarrays of length k. So we will use the similar approach in the previous problem also of taking element and not taking the element. So our problem was 1 2 1 2 6 7 5 1 1 2 1 2 6 7 5 1, and n is 3 they have given, and k is 2. So we need to choose 2 elements at a time instead of 1. As here, like we were doing, like we were choosing only 1 element at a time. But here we need to choose k for this problem 2. So if we branch this out, so what we'll do, we will first choose these 2 because they have given we can choose 2 elements. Right? So this will be something like, so sum will be something like 3 1 plus 2, and rest remaining will be 1 2 6 7 5 1. And if we branch this tree out, so now we have chosen 1 2, and second option will be like don't choose that 2 element. So what will be remaining for the rest? So it will remain 2 1 2 6 7 5 1, right? Because our index book, because we have we have to start from this index and we need to choose k. So here is k. So we have chosen these 2. Sum is 3. And if we don't choose this index, then obviously this index will move to this. From here we need to choose again key element, right? So same. So we have chosen first 2, so it's 3, and if we don't choose, then we have moved to 1 2 6 7 5 1. Again here again same, we have 2 options to choose or not to choose. So if we choose, suppose this 2 we have chosen, so our sum became 5, and the remaining array will become 6 7 5 1. And suppose if we choose that element, and if we don't choose that element, then sum will remain 3, and again our index will move 1 step forward. So now we need to switch from here 6 7 5 1. And similarly for this also, if we choose these 2, so sum will become 3, and remaining will be 3 6 7 5 1. And if we don't choose, then the remaining array will be something like 1 2 6 7 5 1. If we don't choose, then the remaining will be 1 2 6 7 5 1, right? So like this we can branch it out for every sub array. We have 2 options to choose that key elements or to not choose that key element with the same approach. Okay. So that's the only difference between this problem and the previous problem, right? So if we write the code, I mean the recursive code for this problem, what would be? And one more thing to keep in mind in this problem, that n means if we have chosen one subset, for example here n is 3 when we start, but here if we see in this branch, we have already chosen one subset, right? So n will reduce by 1. So here n will be 2. And if we don't choose, then n will remain 3 only. Again, if we branch it out, so now in this we have chosen one subset, so n will again decrease by 1. Here we don't choose, so it will remain 2 itself. And here again, if we follow this branch more, suppose here come again, and again we have chosen 2 elements, so 5 is already there, 6, 7, right? So 6, 7, 13 plus 5, 18, and here will 5, 1, and here if you don't choose, then sum will remain 5 itself, and remaining it will go forward. So now here and it became 0. So right, so now we have chosen all the 3 elements, and we will leg return from here because we don't have any more subarray to choose because n is 0 now. They have especially said we need to choose exactly 3 subarrays. So following this path, if you see here, following this path, we have already chosen our 3 subarrays, and the sum is corresponding 18. So we can't choose further. We have to like stop our recursion here, and we need to move upward. So we can't choose further from here. So suppose now if we write the recursive code for this one, so it will be something like, if we see at every like index we have an option, right, to like whether to include that element or whether to not include that element. So suppose if we include that element, then our recursion will be something like this: index plus 1, we will move one index forward, and we will add the sum, right? What element we have chosen. Suppose that's what we are doing. We are just like choosing one element, 3, summing that element plus moving our recursion, right? Suppose our like index is here initially. We have chosen this element. So for this, the like this index will move here, right? Index plus 1. And we will think, so it will be something like this nums of index plus, if we solve, then it will be index plus 1, right? And if we don't choose this element, then we are not adding this, we are just moving our pointer forward. So it will be like this only, index plus 1, right? And we need to find the max of this, because if we are not including that element, then we are making one path here, right? Here if you see, for each choice we are making one path for ourselves. For example, if we have included that element, then this path we have taken. If we don't include that element, then this path we have taken, right? And from each path we will get one sum if we like further branch it out. Like suppose if we say, suppose this branch, this will return 1, and obviously like this branch will like return another. So we can see for each choice we have, for each point we have 2 choices, whether to include or not to include, and we need to take the maximum of that 2 choices that we have. So here we can say that the max of this will give us the max subset sum. So same we can do like in this also, just we are taking 2 elements at a time. So if we approach the same approach, so what we need to do, we need to add first 2 elements every time. So what 2 elements that we take, we need to sum them, sum of k element. Rest of it, what we will do, we simply do recursion. So here, if you see here, like in this problem, we are choosing exactly one element, but here we are choosing k element. So our index, if we choose that element, then our like index will move to index plus k, right? And since we have chosen this element, so number of subarrays, suppose is then that it also get reduced by 1. And if we don't take that element, then simply the index will be move one step forward, right? And number of subarrays will remain n only. And we need to find the max of these 2 choices. Right? And if we see clearly now, if how can you find out this sum of k? So let's suppose if we look to this problem, if we see we are like adding this sum, right, for each index. So if we start let's suppose 1 2 1 2 6 7 5 1 2 1 2 6 7 5 1. So our index is here initially. Right. So for each index we can find the sum of first key elements for this index, for this index, for this index, for this index, right? So if we compute for like 0, we need to find the sum of first key element for each index, right? So if we start from 0, we can find the sum of first key 0 elements. So if we take for index 0, then sum of first key like element will be 1 2, so it will be 3. If we take index 0, sorry, if we take like index 1, then the sum of first key element will be this, it will be 3 again. So again, if we move forward, our this will be index 2. So if we take here again, it will be 3. Again, if we move forward, then if we can say here, sorry, this will be index 3. So sum will be 2 6 8. Isn't it we are doing here sliding the window for some each case? What I'm saying, suppose here this is 1 comma 2, again for 2 comma 2, and again for 1 2, and again for 3k. So this is sliding window of fixed sum k, right? That's what we are doing here. So this sum for each index we can pre-compute using sliding window. Like this we can pre-compute for each index. Right? So like this we can give the sum of this part we can like easily get. So this will be something like suppose like in our pre-compute array we have computed, so it will be pre and index. Now in the problem they were asking, we do not have to we do not have to return the maximum sum, but like instead we need to return the indices of the maximum sum. So suppose to like from our approach what we have done, we have taken include and not include, right? So like suppose we solve the like our solve function for first we have like a return include, this is the include part, I mean we have included that subset, and our next solve method if we call it will return the not include, we have don't include that subset part. So then suppose we are at index, this index we are at. So like for this index, if include is if our include is greater than or equal to not include, then we can store this index. Suppose in our answer some position will be there and we will store this index here, right? And if we are not taking that element, then simply we don't have to include that particular like index in our answer. Now they're asking for lexicographically smaller, right? Suppose we are at index 2, suppose, and from both include we are getting something like 23, and from not include also we are getting something like 23. Both we are getting. Right. So if we are not including that index, then obviously the rest of our subarrays we will get from something like this index as suppose 4, 5, and 8. Right. This is 100% sure. And if we include that index, then 23 we will get from one index will be 2, right? Because we will take that particular 2. and rest of will be 4, 5, 8, 5, 8. So obviously this is lexicographically smaller, this part 2, 5, 8, then 4, 5, 8. So we can say that if both include and not include are equal, then we need to take the include part. I mean, then like here already like we have done that. If we are making this, we are like already taken if include is greater than not equal to not include, then already we are doing for that particular answer array. We are like putting that particular like index here. So that's why this equal to sign is important to like for us to sort the lexicographically order, to give us the lexicographically smaller order. Now let's move to the problem. So as you can see here, this is the method for finding the max sum. Same approach. If number of subarrays become 0, then we are just returning 0. This is the base case. And like obviously we have two states here, index and number of subarrays. So we have dp to like lessen the number of operations that we do. And here again we are taking the take and not take approach. If we are not taking that element, then simply we are doing index plus 1 nums a and subarrays as we have discussed. And if we are taking that element, then we have already like pre-computed subarrays by 1, right? Because we have already formed one subarray, and we are just storing it, finding the max and storing it back in our DP. And this is used to find the pre-compute. I mean, this is basically the sliding window of constant subarray length k. We are pre-computing each index sum. And this problem and this method is basically just to find the indexes of that maximum sum. So if we see, if we call this method solve that we like already built, so this will give us the maximum of if we include that element, and this will give maximum if we don't include that element. So as you can see, if take is greater than or equal to not take, then we are just storing that index for our answer, and we are moving index plus k, and also decreasing the number of arrays by 1. And if we are not including that element, we are just adding index plus 1, and number of subarrays will remain same. So this problem is basically nothing but just a modified form of max subset sum. In max subset sum, we just find all the sum of length, all subarrays of length 1, but here they have given specifically k. So we need to choose k element instead of 1 every time. And also they have given 3, so we need to choose exactly 3 subarrays, not like in max subset sum we can choose any number of like subset forming that subset sum, but here it's not like that. We need to choose exactly 3. Let's suppose to understand this lexicographically smaller like indexes 1, 2, 1, 2, 6, 7, 5, 1. Right. So if we try to form the subset sum, one subarray sum will be 1, 2 if we take this, and another one can be like 2, 6, and that can be 7, 5. There can be multiples also, but I'm taking these two examples. So if we took this, so here if you see this index, right? So if we see here, we have already included this index. That's why from here we can choose k elements, right? So 1, 2 we have chosen. And if we skip this element, suppose we don't take, so and if we take from here, then it will be like 2, 1. And again, if we take the same path and we like end up with same elements, 7, 5. So from both these two, we will get the same sum, right? So both from both we are getting 23. So if we see here, if we try to manage the indexes of this, so for this the index will be 0, and for this index will be 3, and for this index will be 0, 1, 2, 3, 4, 5. Okay. And similarly, if we take for this, the index will be 1, this index will be 3, 5. So we can see for the same index 0 only, if we have included that index, we are getting 23, and if we don't include that index, then we are getting 23. That's what I'm trying to say here. Include for this part, include and not include part, or this part. So what we came to deduce from here, that if from some particular like index we are getting the same sum, then we need to take what is been included, right? Because if we put this is obviously lexicographically smaller, right? Because we are getting 0, 3, 5 from here. Then corresponding to this from here we are getting 1, 3, 5. So that's what is asking, that we need to like return 0, 3, 5. So if any point, if include and not include comes equal, then we need to take the like indexes of the include part, because it will always be smaller.